Good morning, ladies and gentlemen. Happy Wednesday. Hope you guys are all having a good happy Wednesday. Happy Monday. I hope you guys are all having a good day and had a good weekend. So today, ladies and gentlemen, we are going to be working on the photoelectric effect. So this is a super relevant topic in physics these days because it's this general principle, which is how solar panels work. And I know that's been a kind of hot topic in the media lately with finding alternate sources of energy. So this is kind of how that works. All right. So, ladies and gentlemen, tech problems. Why can't I write? Tablet not plugged in. That might help just ever so slightly to plug in the technology if you want it to work. Success! Plugged in. All right. So, ladies and gentlemen, the photoelectric effect, it is a concept that is going to support the particle theory of light. So this is another one of those big pieces that shows that light behaves both as a particle and as a wave. So how electrons respond to are responding in the photoelectric effect show that light can also behave as a particle. So, ladies and gentlemen, when light is going to shine on a metal surface or your photoelectric surface, electrons are going to leave that metal and they can then travel across a vacuum, and then you can have a detector that'll pick up the current. So remember that current is flowing electrons. Okay, so ladies and gentlemen, how this works is when you're going to have your light shone on the surface, either electrons are going to be emitted immediately. There's no time for these electrons to build and build and build and build, absorb energy. Okay. So how that supports light behaving like a particle is, imagine if you have a bowling pin set up, and then you have a ball, like a tennis ball or something, and you're going to throw it at that bowling pin. Now, if you hit the bowling pin with the baseball or tennis ball or whatever you're throwing, and it falls over immediately, well, there was enough energy in that tennis ball to knock over the pin. So you can imagine the bowling ball as that electron, and the tennis ball as a photon of light. Okay, so a particle of light. And if there's enough energy in that tennis ball, well, you'll get that electron to go flinging off the piece of metal. If there's not enough energy, so if you throw the ball very, very lightly, the bowling pin isn't going to fall over. Okay. Whereas if light was a wave and the wave was being absorbed by that electron, the electron could build and build and build and build and build in energy as it's absorbing more, and then fling off it would go once it's absorbed enough energy. But in this case, light is not behaving like the wave that it sometimes does behave as, or is behaving as a particle in this scenario. So it's as if you're throwing a ball at an object. And if there's enough energy in the ball, it will cause that object to move. So the photon is the ball, and the electron is the object you're hitting with the ball. I like that visual. I think it makes a lot of sense. So, ladies and gentlemen, so you will either have a current detected, or you will have no current detected. Okay, so your bowling pin is either going to move or it's not going to move. Okay, so ladies and gentlemen, every photon is either going to have the potential with one electron and knock it free of the piece of metal, or it doesn't have enough energy to knock free that one electron. Now, big piece here, one photon only has enough energy or enough potential to release one electron. So one photon, one electron. Sounds good? Awesome. All right. Whoops. Scroll down here. There we be. So next part of our theory today, if we don't have any current detected, it means that the frequency is not high enough. Now remember, the higher the frequency of the EMR in general, the higher the energy. Okay, so if we have a frequency that's too low of the EMR, you're not going to be able to knock free an electron. So our frequency, or our definition of our threshold frequency, it's that minimum frequency of that light in order to knock free an electron. Okay. So ladies and gentlemen, now every metal is going to have its own unique threshold frequency. Okay. And it's that minimum frequency required to emit any electrons. So if you get like one electron, well, then you've knocked free gone past your threshold frequency. If the light is below the threshold, that threshold, that minimum frequency of that metal to knock free electrons, then you're going to have no electrons coming through. Okay, no matter how bright that light is. Okay, another key term here we've got is intensity of the brightness. Okay, so intensity, or how bright the light is, it's a measure of the number of photons. Okay, the number of photons. So let's go back to our bowling pin example. The brightness of light is not going to impact how many electrons are going to come off. Let's try this again. It's not going to impact if an electron is going to come off. So if you have that bowling pin and you throw one ball at it, and you throw it with a very small amount of energy and you can't knock it over. So assuming the bowling pin isn't going to wobble and build up momentum, let's say it just stays still, you can throw tennis balls at it one after another, day in, day out, and it doesn't matter how many balls you throw at it with that exact same amount of force, you're not going to knock the pin over. If you want to knock the bowling pin over, you only need one tennis ball with enough energy to knock it over. Okay, it's the same idea. All right, so very, very, very bright, intense light is going to have a ton of photons, but if the frequency is too low, you're not going to knock free any electrons. Okay, now if you are past the threshold frequency, okay, that means if you have a really, really bright light past the frequency, you're going to get more electrons knocked free. So if you have enough tennis balls and you're going to be throwing tennis ball after tennis ball after tennis ball with enough force, well, you can knock over one bowling pin, another bowling pin, another bowling pin, and another bowling pin. So, but you just need enough energy in that throw. Okay, so let's get some highlighting in here. So a very intense source means that there's many, many, many photons. So a photon from a light source that has a frequency equal to or greater than the threshold frequency, the current will increase as the intensity increases. Okay, so that bit is important there. Now, once again, if we have our photons from the light source, they have got a frequency equal to or greater, the kinetic energy of the photons is going to increase, okay, as the energy of that light increases. All right. So here, the energy of the photon is independent from the number of photons. The energy is dependent on the frequency of the light coming in. Now remember that the frequency, when you increase frequency of light, you increase the energy of the light. So the same way your gamma rays have more energy than your radio waves. So, ladies and gentlemen, we can therefore use our law of conservation of energy to solve photoelectric effect problems. Okay, so if light behaved as a wave in this scenario, you would wind up having the energy would increase, of the particles would increase as the intensity increased. So if light was behaving as a wave and we were to increase the energy of the wave, you'd be increasing the amplitude, so how high that wave went. Okay, the intensity of the wave, if light was behaving as a wave, it would mean you'd have a higher amplitude. So think of sound waves. You know, when you have really, really loud music, that would be like the intensity of your music. So the higher the amplitude is, the louder the sound. So the frequency, the speed, and Your wavelength are going to stay the same, but just how loud it is, how big, how tall those waves are would increase. Same idea with light, if light was behaving as a wave in this case. So that would mean when that amplitude is louder, it's going to be absorbing more energy into those electrons. Well, that's not what we see. Okay, the more intense the light, the more photons, the more electrons are knocked off. Sounds good? Cool beans. I nearly said any questions again, guys. We got to get back in the classroom soon. I miss you guys. All right. So, ladies and gentlemen, our photoelectric effect, we're going to look at the conservation of energy. So, ladies and gentlemen, this is our E of the incident light, so the energy of that photon coming in. So if I'm going to go back to the tennis ball example, would be the energy of that tennis ball that you're throwing at the bowling pin. And this is the energy of one photon, okay? One photon. And our EK over here is the kinetic energy of one electron. Now, thinking with the conservation of energy, ladies and gentlemen, is not going to be 100% efficient, okay? So there's going to be some energy needed to knock over that bowling pin, okay? So all of that energy, when you've hit a tennis ball and against a bowling pin, not all of that energy is going to be turned into kinetic energy in the bowling pin, okay? There's going to be some energy lost in removing the bowling pin from where it is, in energy and overcoming the friction of having that bowling pin on the ground. So that's the same idea here with work function. Work function is the amount of energy needed to actually get that electron out of orbit of its protons, okay? So out of its orbital. So that's work function. Okay, so for orbitals, you'll have talked about that in Chem 20. I love Chem 20. It's so fun. It's a great course. All right. So essentially, it's the same as any other conservation of energy equation. Same idea. All right. So here's the notes, ladies and gentlemen, where we talked about work function. So we'll just put a little star beside that. So minimum energy to release that electron from that metal surface. Now, we are going to be making the assumption that the electron is going to have no kinetic energy once it starts, or once it is inside that atom, okay? Now, therefore, our work function, ladies and gentlemen, and the threshold frequency are going to be related to each other. So the amount of energy that electron is going to have is going to depend on the frequency. The work function, ladies and gentlemen, to calculate that is HFO. H is Planck's constant, which is on the back of your data sheet, in either joule seconds or electron volt seconds. Now, whichever one you use is going to depend on the scenario, so watch out for that. Make sure you pick the one you need carefully. Work, W is the work function in electron volts or joules, depending on the scenario. And FO is the threshold frequency in hertz. Okay. All right. Next equation. There we go. Now, our kinetic energy of the particle can also be measured in a different manner. So, because sometimes experimentally, it's kind of difficult to just measure kinetic energy of subatomic particles. I mean, you can't just watch with a stopwatch to get its speed, right? Or you can't attach ticker tape to the back of an electron. Like, that's just not going to work. So experimentally, you need other methods. And thinking back to our forces and fields, remember that charged particles will have, as they're moving, are going to create their own magnetic field. And remember that they're going to have their own electric field. So you can use a potential difference in the interaction of the fields to stop a moving particle. Okay, so, and that's something that you can measure. You can measure a potential difference. So EK max is the maximum kinetic energy that an emitted particle can have. QE is the charge on the electron. Now, unless said otherwise, which it won't be, is you'll find the charge of your electron on the back of your data sheet. So data sheet. And V stop is the voltage required, there should be a D there, required to stop that electron. Okay, so the amount of energy required to stop that electron from moving. So essentially, it's the amount of energy required to slow that down. And we can measure the amount of energy required to stop something, and that would then equal the energy that it has. Go ahead. Yeah. Now, once again, the V stop would then be the minimum voltage in order to stop the particle. All right. So, ladies and gentlemen, you guys ready? Ready to go. Now, all of these equations you can find on your lovely data sheets, and we've got them up here under our quantum physics little section or atomic physics equations. So we've got this guy there, and we've got that guy there, and then we've got our equation from last day. So today we're going to be using all three of these equations. So make sure that you guys can see them or find them. Pull out your data sheets, highlight them, underline them, what have you. Okay. So, ladies and gentlemen, our threshold frequency of a particular metal is that many hertz. So our FO is 1.14 times 10 to the 15 hertz. The frequency of bad physics jokes just hurts. What is the work function of the metal? Okay, well, ladies and gentlemen, what we've got here is our lovely equation. Work is equal to FO times our H. Well, and your data sheet is the other way around, but it doesn't really matter. There we go. So, well, we have H as Planck's constant on the back of your data sheet. And in this case, it doesn't particularly matter whether we use electron volts or joules. So let's use electron volts. Why not? So our frequency is 1.14 times 10 to the 15 hertz. There we go. That really came out super messy. That's really bothering me. Let's fix this. There we go. And then you're going to find Planck's constant on your data sheet. It would really help if I would write things down properly. Okay, there we go. There we go. There's Planck's constant. Multiply our lovely values together. And of course, sig digs, as always, this one we want 3. So 4.72 electron volts. Nice little warm up for us. Get our brains stretching on Monday with a nice little easy calculation. All right, let's move on. More tricky questions. Yes. Challenge the brain. All right, ladies and gentlemen, electrons are ejected from a photoelectric surface with a maximum kinetic energy of that many joules. All right, so EK max is equal to 1.92 times 10 to the power of negative 19 joules. Now remember, that's the energy per electron. If the incident light has a wavelength of that many nanometers. All right, now remember, ladies and gentlemen, we have to convert that into meters. So 4.10 times 10 to the 2 nanometers. And we're going to multiply that by our 10 to the negative 9 meters divided by our 1 nanometer to convert our units. Nanometers cancel. We're left with meters. And our lambda, ladies and gentlemen, 4.10 times 10 to the negative 7 meters. All right. And what is the threshold frequency of the photoelectric surface? So, ladies and gentlemen, the second we're going to be dealing with a photoelectric surface, our strategy, the best place for us to start is our conservation of energy. All right. So, our equation for the conservation of energy in this case is our incident light is going to equal our energy out. So the energy in the incident light is going to equal the energy leaving. And in this case, the incident, the light of the incident, energy of the incident photons is going to be equal R EK max, plus our work function. Okay. So, ladies and gentlemen, we have that we've been given a value of EK max, and we have an equation for this guy. Now, remember, ladies and gentlemen, we do have an equation for this guy as well. Okay, that's our equation that we looked at last day in our last video. So I'm going to take the energy of this photon from my last equation, which is hc lambda. So the energy of that photon is going to equal hc divided by lambda. Okay, so I am then, and my EK max, well, that's a value that I've already been given. Okay, and my work function, ladies and gentlemen, is going to be my HFO. Okay, I have been asked to find FO. So I'm going to need to rearrange this equation here, so then that way I can get HFO on its own. We do reverse bed mass, so I'm going to subtract EK max from both sides, and my HFO is going to equal my let's help if I write this out properly. It's Monday, and it actually is Monday tonight. All right, so my HC over lambda minus EK max. There we go. That's how it needs to be written. So what we can always do is you can either divide all of this by H now, or you can solve for this thing here and then divide by H after. Let's do that. It'll be less messy. A little bit easier to read, and mathematically it's going to be the same anyway. All right, so our HFO is going to equal HC. So let's think for a moment here, ladies and gentlemen. Why can I not cancel out these two H's? They're not in both terms on this side. Okay, if H was in both terms, then we would be able to cancel out the H's, but H is not here, ladies and gentlemen, so you can't cancel out H. All right, so ladies and gentlemen, our H, value of H, 6.63 times 10 to the negative 34 joules, and times seconds times R3 times 10 to the power of 8. Divide that by our lambda of 4.10 times 10 to the power of negative 7 meters. Now the EK max is a value we've already been given of our 1.92 times 10 to the negative 19 joules. All right, so our HFO, ladies and gentlemen, is we're going to get us 2.9312 times 10 to the power of negative 19 joules. Now, ladies and gentlemen, when you're solving this in your calculators, remember, solve this first. This times this, enter. Divide by this, enter. Minus this, enter. If you don't do this properly in your calculators, you're going to get the wrong answer. Okay, garbage in, garbage out. So now that we have our HFO, I'm going to divide both sides by H. And that is going to give me my value for that lovely threshold frequency. So I've got my 2.93 ... times 10 to the negative 19 joules. And I'm going to divide that by, remembering you have to use the Joule Planck's constant here, 6.63 times 10 to the negative 34 joule seconds. Now look at the units here. The joules cancel and we're left with 1/seconds, which is equivalent to hertz. Okay. So, ladies and gentlemen, we wind up with 4.211 ... times 10 to the 14 hertz. And with our sig digs, 4.4, I dropped a 4, goodness, 2 times 10 to the negative 14 hertz. There we go. Cool beans. All right. So, ladies and gentlemen, we're going to go on to the next question here. All right, number 3. Okay. So for this one, our work function of silver is that many electron volts. 4.72 electron volts. The electromagnetic radiation with a wavelength of our 2.5 times 10 to the negative 7 meters, sweet, right units, don't have to converge, strikes a piece of silver. Determine the speed of the electrons emitted from the piece of silver. All right, so let's think for a moment. Ladies and gentlemen, we are dealing with energy, conservation of energy, and we're dealing with speed. We also have EK max in here. Well, this is where we're going to bring in our 1/2 mv squared. Okay. Now, ladies and gentlemen, when we go to work with 1/2 mv squared for equals EK, we have to have our energy value in joules. We can't have that in electron volts. So we are going to have to convert our electron volts at some point in the equation into joules. So watch out for that, okay? All right. So, ladies and gentlemen, we are going to need to find the EK of said electron. So that means we can then find the speed. So when we want our energy equation, energy in is going to equal our energy out. So we know that law of conservation of energy. So our incident energy is going to equal our work function plus the EK max of that electron. Well, if we're going to be finding the speed, we need to find our EK max. So I'm going to subtract work from both sides. So that's going to equal my incident energy minus, that should be a minus, not an equals, the work function. Well, we have the work function, so we don't need to break that down into its other equation. But the incident energy of that photon, we are going to need to break that down. So this guy is going to be hc over lambda minus work function. So if you really wanted to, one possible way to do this would be to convert this guy into joules right now, and then have your 1/2 mv squared here, and then rearrange the equation in its entirety to then isolate for your V. I know some of you guys love doing that, so we're going to do this a couple different ways. I'm going to solve this first by finding EK max, and then putting that into 1/2 mv squared. And then after that, just for fun, because we can, we will then put 1/2 mv squared in here, and we'll just rearrange the formula, because why not? All right, so our EK max, ladies and gentlemen, is going to be our now this one we have to use our electron volts here, because this is here. I'll convert to joules after. So the H has to be electron volts here. I'll convert to joules after. there's a negative 15, that's our electron volt seconds, times 3 times 10 to the power of 8, divided by our wavelength of our 2.5 times 10 to the power of negative 7. We're going to minus that from our work function, so 4.72. I'm going to scroll down here. There we go. And I'm going to wind up with an EK max of our 4.968 electron volts minus from the 4.72 electron volts, which is going to give me 0.248 electron volts. Now, ladies and gentlemen, as I mentioned earlier, 1/2 mv squared must be in joules. So I need to convert this into joules, and your conversion factors on the back of your data sheet, so 1.6 times 10 to the negative 19 joules divided by 1 electron volt. EVs cancel. I am left with joules. So my EK max, ladies and gentlemen, in joules is 3.968 times 10 to the power of negative 20 joules. Let's think for a moment. Why does it make sense for us to have such a small number for kinetic energy? The mass is so tiny. Exactly. Teeny tiny mass, teeny tiny kinetic energy in comparison to an object of a larger mass. Okay. So, ladies and gentlemen, now I can take my EK as equal to 1/2 mv squared. I can then rearrange this equation to my V is equal to 2EK divided by M, root the lot. I assume you guys can figure out how to rearrange that equation. We've been doing this since grade 10. So then we've got 2 times our EK in joules, so 3.968 times 10 to the negative 20. Okay, divide that by the mass. Now the mass of the electron, that's a constant. You get that from the back of your data sheet. Okay, square root the lot. And you are going to wind up with a speed of your electron of 2.95 times 10 to the 5 meters per second. Sounds good? Awesome. Now, as I promised, just for fun, let's go back up here and put some numbers into this half of the equation and then rearrange and solve just because we can, because it's good practice. So 1/2 mv squared is our EK max. Now, in order to do this method, you need to convert this into joules now, okay? So we are going to have EK max 1/2 mv squared is going to equal HC over lambda minus W. Okay, well, I'm trying to find V here, so I'm going to multiply the lot by 2 and divide the lot by M. So my V squared is going to equal 2 times HC over lambda minus W. And then you divide the lot by M. Okay, then to get rid of that, you're going to square root both sides. There we go. So, ladies and gentlemen, we wind up with a lovely derived equation. I know some of you guys really enjoy doing that and prefer that to all of these other little steps. So I am perfectly okay with whichever method you pick. We'll make this neater once we get that canceled. So whichever method makes your heart sing, show your work and make sure you're using appropriate physics concepts, and I am happy. There we go. All right. I love doing this method. When I look at equations like after the deriving them, it's like, wow, I feel so smart. So it's fun. So ladies and gentlemen, for that equation, the challenge with this is you're going to have a bit of a pain in the butt of putting it into your calculator. So you would have to put this times this, enter, divide by this, enter, minus this, enter, times 2, enter, divide by m, enter, square root, enter. So putting it in your calculator is a pain in the butt, but you have less writing to do. I love that. That blue equation is just so pretty. All right. Once again, either method, I don't care which one you use. You can use the red method. You can use the blue method. I don't care. Show your work. Put your answer in correct units and sig digs. Okay. Last question of this particular video, ladies and gentlemen. Okay. This one's not too bad. Okay. All right. So, ladies and gentlemen, a light source with a frequency of that many hertz, 6.65 times 10 to the power of 14 hertz, shown on a piece of copper. In order to bring the emitted photons to a stop, a voltage of 0.48 volts is required. So, that's our V stop, 0.48 volts. All right. What is the speed of the emitted electrons? All right. Ladies and gentlemen, as soon as we're shining light on a piece of copper, that immediately tells us that should be a P. We're going to be looking at the photoelectric effect. Okay. So, ladies and gentlemen, once again, we've been told that we're trying to find the speed, so we want to find kinetic energy. Now, in order to find our kinetic energy, well, we have the V stop here. So what we are going to do is we're going to use this equation. Our EK max is going to equal QE V stop. Now, what's also kind of cool about this, ladies and gentlemen, let's pull out our data sheet for a sec. You guys remember this equation right here? Well, look at that one. Delta V is equal to delta E over Q. And that's the strength of our electric field. So what's happening with this here, ladies and gentlemen, is we are bringing in our two concepts together. I think it's really cool. I love it when stuff like that interacts. It shows how complicated the world really is. Okay, so we've got this equation here, and then we are trying to find the speed, so that means we're going to need to find this. Once again, I'll do the other, this method, I'll do the expanded method, and the other one will do the deriving the equation by substitution. Okay, so for this one, EK max, need to find that. Now, once again, we have to have everything in joules, ladies and gentlemen, because we want our kinetic energy. This equation also creates energy in joules. So, ladies and gentlemen, our Q of our electron, that's a constant. Okay. That's on the back of your data sheet. And then we are going to have our V stop is going to be lovely value of 0.48 volts. Our EK max is 7.68 times 10 to the power of negative 20 joules. Well, now I have this, I'm trying to find the speed. I can once again use my EK equals 1/2 mv squared. And I'm going to then rearrange this to get my V. Okay, once again, I hope you can manage rearranging that equation by this point. And then V2 times our answer, 7.68 times 10 to the negative 20 joules. That's small joules. There we go. Divide that by mass of, once again, electron constant. From your back of your data sheet, 31 joules. Root the lot, and we wind up with your speed of with your sig digs and units and all of that jazz. 4.11 times 10 to the power of 5 meters per second. Bam. All right. That's fun. It's always good. What's about the frequency? What can we say about the frequency? Distractor. The frequency is a major distractor. I know it hurts the soul so much that the frequency is a distractor. Yeah. You guys are going to be so sick of this pun by the time we're done this. Do you guys like the pun on the front of your assignment? The bellboy at the front of the hotel says, "Oh, hey," says to a photo, "Oh, hey, can I help you with your luggage?" And he says, "Nope, thank you, I'm traveling late." Get it? Yeah. Okay. So, ladies and gentlemen, let's look at the alternate method of making one lovely big equation via substitution. So I'm going to take this equation here, and I'm going to substitute my EK max with my 1/2 mv squared is going to equal QEV stop. And then I'm trying to find V, so once again, multiply 2, divide by m. So I'm going to wind up with, whoopsie, it's not where I want that. I am going to wind up with my V squared is going to equal 2 QEV stop. And I'm going to divide that by the mass, and then I square root both sides, and we wind up with 2 QEV stop divided by mass square root. There we go. So once again, I don't care which method you use whichever one makes you happy. This one, once again, is going to be more of a pain in the butt to put in the calculator, and this one takes more writing. I don't care which one you do. Do whichever one makes you happy. Show your work. Units, sig digs. We're golden. All right. So, ladies and gentlemen, practice problems for you guys to do are there. Give some of those a shot. All right. Now, there's this question here. This is also a really, really good question. I actually want to go over this. I like this question. Okay, so we're going to do this one here, and then we'll call it with the video. And then I'll do a second video for our next piece on the photoelectric effect, which is your favorite graphing. What I actually would advise you to do is try that graphing question, that second one, the big example question on the back. Give that a try, and then watch the video, and then see how you guys do. Check your answers. You guys are already rock stars with y equals mx plus b. So. All right, so this one's a theory question, ladies and gentlemen. This is an old diploma question, so if we had old diplomas, yeah. I'm new, I'm bummed we're not in class 2. All right, so ladies and gentlemen, classical wave theory and quantum physics make different predictions about the effect of incident electromagnetic radiation on a photoelectric surface. So what we're going to do is we're going to match to see what would make sense about classic wave theory and about quantum physics. So what I want you guys to do, pause the video, try this question, then restart the video and check your answer and check to see if your prediction was right. So, and stop. We're back! And the video didn't die when I did that, like a couple videos ago. Oh man, that was funny. Well, now it's funny. It wasn't at the time. 4 days to get that video out. Okay, so ladies and gentlemen, classical wave theory. So what we're going to do for this one, there's several different methods you can go with numerical response. You can find the blanks and then go and read the pieces and then put which one's in the blank, or read the pieces and then plonk them into the blanks as you go. For this question, because there's a lot of text with these and there's going to be a lot of thinking with each of them, I'm going to read them and then plonk them into the appropriate spots. Okay, so for number 1, low intensity electromagnetic radiation on a photoelectric surface for long periods of time will cause photoemissions. Okay, now that one, let's think for a moment. Let's go back in the notes. Go back on your notes. Does that actually happen? No, we have a threshold frequency. Now remember, the frequency is relative to the energy, okay, or as a measure of the energy. So if you shine low intensity light on a photoelectric surface for it doesn't matter how long, you are not going to get any coming off. That supports the particle theory of matter. Whereas this question number 1 here, that's what you would see if a wave is if you're shining a wave onto a surface and it absorbs the energy, absorbs. The energy will build and build and build and then go. Okay, so that, what we would see here would fit with wave theory. Now, 2, high intensity electromagnetic radiation will not cause photoemission unless the frequency is greater than the photoelectric surface threshold frequency. Okay, that's exactly what we talked about. This is what we know happens, and that is why it supports our quantum physics model. Okay, so ladies and gentlemen, energy of the emitted photoelectrons will increase if the intensity of the electromagnetic radiation is increased. Okay, let's think back to this one. Remember that according to the quantum physics definition, that intensity is equal to the higher the intense the light, the brighter the light, the more electrons are coming. So that means if you're going, like, think of those tennis balls. It means that you're throwing more tennis balls, you can knock over more bowling pins. But just because you're throwing more tennis balls, does that mean that the electrons coming off are going to have more energy? Not according to the particle model. According to the wave model, that would then make sense. Because in the wave model, the intensity would be your amplitude. Okay? And then the higher the amplitude, the more energy, and therefore the more energy those particles would have coming off. Okay? So 3 is going to fit with classical wave theory. All right? And then number 4, the energy of the emitted photoelectrons is independent of the intensity of the light. That is true. Okay, the energy emitted by the photoelectrons is dependent on the energy of the incoming photons. Okay, so this one independent, so separate from the intensity of the light. The number of electrons is connected to the intensity of the light, so the current. All right, ladies and gentlemen, that is this video. I hope that you guys have a good day today. No fires, injuries, or explosions. And put on sunscreen. It's warm out. Okay, you do not need to be burning yourself through the particular wave of EMR called UVA and UVB. Cool. Have a good day, guys. And I need to figure out where the stop button is. I think I would figure out how to stop this thing by now. Come on, computer. And stop. Have a good day, guys. Bye.